Welcome back to the course in Nuclear Medicine Physics. Today we're talking about radiation safety and dosimetry. Now, the dose of radiation in some volume of mass m is E divided by m. It's the energy deposited per unit mass. Now, it turns out that not all doses are equal. You could have the same dose from two different types of radiation, and one could be far more damaging than another. For example, alpha particles, which are helium nucleuses, are far more damaging than gamma radiations at the same dose. This is due to the fact that they ionize molecules in the body differently, and what you really have to look out for is double strand breaks in the DNA. In addition, depending on where you get irradiated in your body, it can be more damaging in some places than in another. Take into account the fact that at the same dose, different types of radiations are more damaging than others, and different areas of the body are worse to get radiated than others. We've defined two quantities. These are known as the effective dose and the equivalent dose.
Okay, so now we're gonna switch topics a little bit. We're gonna talk a little bit about dose and some biological considerations. Still not gonna see how is that we perform dosimetry in nuclear medicine. We're gonna leave that for our next lecture. But let's try to understand what is dose. I'm gonna acknowledge Dr. Anna Seller because she has provided me with some of the material that I'm gonna present in these slides. So let's start talking about dose. Well, the Committee on Medical Radiation Dose is typically abbreviated as MIRD, was formed in 1965 and has the mission to standardize internal dosimetry calculations. So the MIRD committee is what deals and what standardizes what we do for dosimetry in nuclear medicine. But what exactly is dose? And dose is a quantity that is defined as the energy deposited in a target region. It can be, let's say, an organ or a tumor per unit mass. So again, what you see here, so the dose is you deposit some energy on some tissue, and that tissue has some mass. The energy that was deposited there is dose. So the standard units of absorbed dose is the joule per kilogram, and 1 joule per kilogram has been called 1 gray. So when we talk about grays, we're talking about dose. Now, some biological effects of acute total body radiation. So acute means you have this dose in a short period of time and then the dose is not there anymore. So when you get an exposure of about 50 milligray, there's typically no detectable symptoms or injury. When people get about 1 gray can cause nausea and vomiting maybe for 1 or 2 days, or maybe there's a temporary drop in production of new blood cells. When you reach the level of 3.5 gray, there's typically nausea and vomit initially. Then this is followed by a period in which it looks like people are getting better. There's wellness, sorry, I think I have a typo there. But then 3 to 4 weeks later, there is a potential for deficiency of white blood cells and platelets. Typically, there is medical care required, and maybe it can be fatal. And exposures of more than 3.5 gray, people typically need medical care, and it can be fatal. So, of course, we don't want to be exposed to too much dose. Now, most of these values typically come from observations done in Hiroshima and Nagasaki after the atomic bomb was there and people were exposed to radiation. So that's why we have this ALARA principle, and ALARA principle is basically saying that radiation doses should be kept not only within legal limits, but also as low as reasonably achievable. And that's where it comes the ALARA. So ways of minimizing dose is by increasing the distance from the source. And we saw back in the days when we're talking about detectors, how that solid angle of the emissions, basically the amount of particles crossing an angle falls with r squared. So it's inversely proportional to r squared. So the further you are from the source, the less radiation you're going to be getting, the less dose you're going to be getting. If you stand up beside your source for a long time, then again, you're going to get more of those emissions. So decreasing the time of the exposure is a way of minimizing the dose. Another way is, of course, using shielding. You're trying to block those particles from reaching you. An example of shielding in nuclear medicine, so typically nuclear medicine technologists are often required to use aprons, so they wear something on top of their bodies. They're typically lead aprons. There are different types of aprons. There are lighting materials that can be used for X-rays. If you go to a nuclear medicine department, yeah, typically those are true lead aprons that should be used by those technologists. And to put you an example of reduction from, okay, well, let's think we're taking some lead equivalent apron with 0.5 millimeters thickness, then this is how that reduction of the exposure would look like. So for example, if you look for technetium 99M, which again is the isotope most commonly used in the nuclear medicine department, it has energy of 140 keV photons, and you use this apron, you're going to be reducing around 70% of the exposure. So the number of aprons that you would need to reach 1/10 value layer, back in the days we talked about 10th value layer, but that means you want to basically attenuate 90% of the photons. So you only want to keep 1/10 of the initial photons. You will need 2 of these aprons. And these these 2 aprons will weigh around 15 kilograms. Now, scattered X-rays, one of the aprons typically reduces your exposure by more than 90%. So 1 apron is enough to reach your 10th value layer. It weighs around 7.5 kilograms. But when you go and look at cesium-137, which is an isotope of 662 keV photon emissions, this type of apron will only reduce you by 6%. So you will need 36 aprons to reach 1/10 value layer. That's like basically putting 207 kilograms of clothes on top of you, which of course is too heavy. So so look, technetium 99 is common to use aprons also for the scatter, but if you think about a PET department, in PET, we've seen that we deal with photons of 511 keVs, that's closer to cesium. Those aprons won't really do much for you. So when you walk around a PET facility, the technology is there. You won't really see them wearing aprons. Aprons won't really do much for that. So what we do in a PET department is we try to decrease the time of exposure and increase the distance from the source. So technologists will go and inject patients, and hopefully they won't stay beside the patients for too much, and they will try to stay as further away from the patient as they can just to reduce their exposure. Now we talked about dose. So there's this other definition. It's called equivalent dose. Now absorbed dose in tissue that takes into effect the biological effect of radiation. And by this I mean stochastic effects. Now in radiation you have, I forgot the word. Deterministic effects, in which you put a dose and you immediately see an effect. Those like the ones I was talking about. But there's some other effects that are stochastic. It's like it might happen to you or it might not. So for example, we know the effect that exposing yourself to radiation can cause cancer. That's a stochastic effect. Maybe it's just by pure chance that you get cancer or not. Now, it's of course thought that the more exposure to radiation you get, the higher the chance of getting cancer. But it doesn't mean that. I mean, you can have 2 people being exposed to the exactly same amount of radiation. One of them gets cancer, the other one doesn't. It's just a stochastic effect. But when we take into account those biological effects of these stochastic effects, then there have been some definitions of radiation weighting factor, and there's the RCRP. It's an association that looks into, they have done investigations and they have put these weighting factors for us to know. So for example, they say, okay, the weighting factor when we look at X-rays is going to, at X-rays, gammas, betas, and electrons is going to be close to 1. But if we're going to irradiate with protons or neutrons, maybe the biological effect is 10 times higher. So what I mean with this is, for the same dose of radiation, you would have a much bigger biological effect. When you use alpha particles, ICRP 60 and ICRP 103 publications used to deal with weighting factor of 20. Now, new publications have been bringing that and saying, okay, no, this is more like a factor of 5, but still more investigation is needed. And what I mean with this is, at least even in nuclear medicine, we need to still understand much better the biological effects of the dose rates of our therapies. For example, we inject radiation into patients, there's radiation, but the dose rate is not as high as when we use external beam radiotherapy. This will give chances to cells to repair. I think I'm going to touch that in a moment, but we still don't fully understand it. So these are the accepted weighting factors as of now. But just think, alpha particles can damage the DNA much more than a beta particle. So that's why you see a much bigger biological effect when you deal with the same dose. So equivalent dose is measured in units that we know as sievert. That's the standard unit. And the equivalent dose is the absorbed dose in gray. You multiply by that by the radiation weighting factor, and you get the equivalent dose. And now, when we multiply by this factor, you basically change the unit from gray to sievert. But again, a sievert is still, I mean, those weighting factors are dimensionless. Your sievert is still joule per kilogram, or energy per mass. We have an extra unit that is called effective dose. And the effective dose is the absorbed dose in tissue, taking into account the biological effect of the radiation and the fact that some organs may be more sensitive than others. So then we also come up with what we call the tissue weighting factors. So I'm adding another factor here. So effective dose is absorbed dose times the radiation weighting factor, that's equivalent dose, times the tissue weighting factor, then now we have effective dose. And the units are also sievert. So let me show you just ICRP 103 publication has come up with the tissue weighting factors that we mostly accept currently. And they have assigned these values. So for the gonads, they have a value of 0.08. Bladder, for example, is 0.04. Bone marrow is 0.12. And all the remaining tissue, bone surfaces are 0.01. When you add all those factors for all the different organs, that gives you a total of 1. Now, of course, if you add these values here, you're not getting 1, is because, I mean, bladder and esophagus, you have to multiply this by 2. If to the liver, you multiply this by 3, and so on and so on. But the total sum of that should be 1. Now, the ICRP look at the different probabilities for the occurrence of the stochastic radiation effects in various organs and tissues, and that's how they've come to suggest those factors. Yeah, and just basically giving you the probability of an occurrence of one of those radiation effects on a given person. Now let's look at some biological considerations. Well, we talked about linear energy transfer back in the days, which is the amount of energy transferred by a charged particle to the medium per unit distance. And there's this other thing that we define as specific ionization, which is the number of ion pairs produced by a charged particle per unit of travel distance. So biologic effects of radiation include, for example, chemical changes. There's some chemistry changing inside your body because of radiation. It changes your DNA. It can change your proteins. It can produce free radicals that then they combine with other atoms or molecules to produce something that might not be good for you. It can alter our chromosomes, and then if we alter our chromosomes, we can have some mutations. Some mutations might be good, but some of the mutations can cause cancer, for example. It can alter the cell cycle, and it can induce cell death. So all these are effects of radiation. That's what we're trying to take care of it. Now, cells can repair certain levels of cell damage. So for example, there's natural radiation, is what we call the background radiation. And those are easily repairable by cells. So there are mechanisms in the cells that go checking the DNA, and they make sure they can replace parts of the DNA that are missing, or it can be repairable. Now I'm taking this graph from the fact sheet that you can find in this link, and you'll have it in the PDF. That is a natural background radiation published by the Canadian Nuclear Safety Commission. But this just gives us an estimate of how we get radiation in our bodies just by natural sources. So just by breathing, we can have maybe 0.9 millisieverts in a year. And by breathing is because down in the air, there might be radioactive gases. That is just part of nature. Ingestion, so for example, the typical example is when you eat a banana, and banana has potassium, and there's some isotopes of potassium that are radioactive, you just end up eating some radioactivity. The cosmic radiation is, well, there's radiation coming from the sun and from space that might end up reaching us. That can contribute a little bit to that. Again, terrestrial radiation, again, there might be rocks or something in our surroundings that can contribute to some radiation. Again, from the same publication, there's just an average annual effective dose from natural sources. It depends a lot on where you live. So for example, if you live in Kerala coast in India, you can expect you're going to have 12.5 millisieverts a year of natural background radiation. Like here in Vancouver, where I'm based and some of us are based, we can expect about 1.25 millisieverts from background radiation. So, and then I'm just breaking it a little bit. We can expect 0.28 millisieverts from radon, 0.26 millisieverts from cosmic rays, 0.3 millisieverts from the Earth, 0.35 millisieverts from like internal, something that you ingest, like bananas, and approximately 1.2 millisieverts in total. This is for Vancouver. In terms of medical procedures, now these are not natural sources. Now we have equipment that creates some of this radiation. When you have a chest X-ray, well, you can have a little bit of a dose. And I'll let you guys look at that table. We'll see that a pelvic CT will give us around 9 millisieverts of radiation. In terms of nuclear medicine procedures, again, we're covering a wide range of doses, but just think about a PET scan will typically give you between 6 to 8 millisieverts. And I would say the average here from all these procedures, I would say something around 4 millisieverts, something like that. But if you want to look more in detail of what type of exposure, what type of dose do you get from different nuclear medicine procedures, then there's this nuclear medicine radiation tool from the Society of Nuclear Medicine and Molecular Imaging. You can find it, the link is there. But it's easy, you just go and select a nuclear medicine exam. You can more or less select how much activity you are including and the type of model. I mean, of course, there are models for adults, there are models for kids, and it will give you a value here, the radiation dose estimate. So tell, based on the input that you gave me, in this particular scenario, I can think that there's an effective dose of more or less 8.4 millisieverts. But you can go and give it a try for many different procedures. That's of course not personalized. It's just taking like the average human.
And again, to remind everyone, because the weighting factor in nuclear medicine, gamma rays, X-rays, and electrons and positrons is 1 sievert is 1 gray. So you can always remember it like that. But except if you're doing alpha therapy of some sort. But for imaging, as we do, when you see a number like sievert, it's the same as gray. Correct, Carlos?
Yeah. There's some radiation dose limits. So in Canada, because I'm based in Canada, but of course you guys are some not in Canada, so we'll have to go and find the laws of the particular location you live with. But here in Canada, we have the Canadian Nuclear Safety Commission, which is our federal agency that regulates nuclear facilities and nuclear materials in Canada. And they're responsible for setting radiation dose limits that protect the workers, like, for example, the nuclear medicine personnel. For example, me as a medical physicist, the nuclear medicine technologist, we need to protect them from overexposure to those radioactive sources that they work with. But they also set the dose limits to protect the general public, and we need to protect the general public from overexposure to radiation from some of these facilities that we know will be dealing with radiation. Sorry, is there a question?
Yeah.
Okay, so for example, the prescription limit for the general public is that in 1 calendar year, no person should get more than 1 millisievert. Okay, but then I just showed you that background radiation gave us more than 1 millisievert. So how can people get less than 1 millisievert? Okay, this 1 millisievert is that people should not get more than 1 millisievert because of those artificial facilities or handling radiation that we know we are doing. And there's a definition for a nuclear energy worker. We refer to them typically as NEWs. And I'm quoting the definition from the CNSCs. Means a person who is required in the course of the person's business or occupation in connection with a nuclear substance or nuclear facility to perform duties in such circumstances that there is a reasonable probability that the person may receive a dose of radiation that is greater than the prescribed limit for the general public. So for example, I'm a new because I work in the nuclear medicine department in the clinic, because I will deal with radiation. There is a probability that I can reasonably get a higher exposure than 1 millisievert. So that's why I've been qualified as a new. And this is the last slide that I'm gonna have for today, but these are basically the dose limits. So NEWs, nuclear energy workers, shouldn't get exposed to more than 20 millisieverts per year. And the general public should not get exposed to more than 1 millisievert. Now, there's also limits for particular organs. So for example, the lens of an eye, and we shouldn't be exposed to, well, NEWs shouldn't get more than 150 millisieverts to the eyes. The general public should not get more than 15. The limit for the skin is 550, and for the hands and feet is 500 millisieverts and 50 millisieverts. Yeah, I don't know. Are there any questions about this? We'll finish then on Thursday when we jump into internal dosimetry.
If I could simply add a comment, there's increasing public awareness about dose and the significant doses that people have had the impression that is being delivered to patients, let's say from CT scanners and let's say other modalities, nuclear medicine, etc. So there's always a balance, right? So if you're very, very effectively treating cancer patients using imaging, obviously, that small, tiny added risk is absolutely worth it. But the point is, you don't want to do unnecessary imaging. You don't want to overexpose the patient. So there's been significant efforts in this area and concerns. And, nowadays when a new, let's say, advanced image reconstruction shows up, you could, of course, use it to make the images better, but there's more interest in perhaps making you require less injections, so lowering the dose. So there's an image wisely campaign for adults. There's an image gently campaign for in pediatric imaging. So there's been a lot of public awareness in this area and concern, though sometimes there's been overreactions in this case. But it's good. It's a great dialogue that is happening. And so our job is to make sure that we're not unnecessarily exposing patients to radiation. And so there's significant studies and efforts in this area.
So yeah, so basically when we treat patients, of course, you just don't go and give radiation just because. I mean, radiation can cause cancer. We know that. That's a stochastic effect. But we also know for a fact that radiation can destroy cancer cells. So in a patient that has high advanced cancer, well, the benefits of radiation to kill those cancer cells outweigh the risks of getting cancer, for example. So, well, of course, yeah, it's always looking at the benefit and the risks versus the benefits, and we make those compromises. And most of the patients that get cured from cancer in the world are cured by radiation therapy. So we know it works. Okay.